Thread calculations are sometimes necessary on the job. When you don't have the actual fasteners with you, you're going to be getting those in 3 days time, but today you have to drill some holes and cut some threads. So I'm going to show you how some of those calculations, two of those calculations are done. We're going to calculate clearance hole size and tap size. I'm going to use metric and imperial, so you can see both. Let's see a clearance hole first. The clearance hole is the idea that you need to drill a hole through which this fastener will slide through clear, something like that. The smallest clearance hole needs to be determined, so you know what's the smallest drill bit size you can get away with. In this case, I just grab this sleeve to demonstrate the hole. You can see there is quite a gap between the two, so there's lots of clearance between the two. The idea of a clearance hole calculation is, again, to figure out what's the smallest possible hole you can get by. You could just drill a hole with the nominal diameter of the fastener, but nominal diameter is not the same as actual. Here, take a look at this one. This is a 7/16 bolt, and if I clamp it in there, it's not 7/16 of an inch, it's 55/128 of an inch. And the equivalent fraction for 7/16 of an inch would be 56/128. And now you see that the actual bolt is smaller than 7/16 or 56/128. It's smaller by 1/128. Now, there are no drill bits that come in there. See, now I made it bigger. There's 7/16. So there are no drill bits that come in 128th of an inch size. But just work with the concept here. You know, in this case, you would just need to drill. Oh, where is that size? Where is it? You would just need to drill, you know, a 7/16 hole, and that will be perfectly fine. So if you drill with the nominal diameter or nominal size of the bolt, but that doesn't always work really well. So without further ado, I'll just show you the thread geometry here. There, it's the same thread geometry for metric or imperial bolts, so that's the good news. And on this one, you can see that both thread angles are 60 degree, metric or imperial, and you can see that the top of the thread is truncated. It's not sharp. It's not a sharp triangle there. The tip of the triangle there is missing and is rounded off a little bit. This calculation that I do here is going to be approximating a clearance hole size, because I'm not going to allow for that little rounded part. That rounded part has a radius. I'm going to ignore it. Okay? So I'm just going to count and calculate down to that solid black line there, as if that rounding didn't exist. You can see that the amount of rounding here on the edge is expressed in terms of H, thread height. And this picture here says, there, you can see it, that H is the height of the thread, and that little truncation there is 1/8 of the thread height, or height divided by 8, you know, 1/8 of the thread's height. You can see on this one that the threads are indeed not sharp, they are rounded, and you can see that they are not sharp triangles. Okay, they have a little rounding, and you can see this wide, not so wide, okay, you can see a little width that the tip of these triangles have, okay, and that, you know, happens on every thread. So to do this, you need to calculate the height of the thread, but you don't have it. But you can calculate it, because it's a 60 degree thread, that you take the pitch and you times it by 0.866. That number is intrinsic to this triangular thread that I'm going to try to do my best to do an equilateral triangle here. This is a 60-60-60 triangle, okay, and that 0.866 is cosine 30. Now cosine 30 comes about when I chop this one in half. Now I have a 30-60-90 triangle, and cosine 30 relates the length of flank here to the height of the thread when we are having the 30-degree angle as our reference angle, and that's where that 0.866 comes from. And why we're multiplying with pitch when I just said this is the flank and that's the height of the triangle, because it's an equilateral triangle and pitch is the distance from crest to crest or from root to root along the thread. So if this one is pitch, equilateral triangle means all sides are the same length. If that one is pitch, that one is also pitch, that one is also pitch. So it's pitch and height that's related. That's what the cosine 30 is. So now I drew over it, but you get the idea. So in case of a metric thread, metric threads are fairly easy to do it with, because you've got the pitch is part of the thread designation. Here, take a look at this one. Okay, there on a metric thread designation, M10 by 1.5. The 1.5 is the pitch in millimeters, and yeah, so there is metric sizes. So how about M20 by 2.5? How about that one? Let's calculate that one. If we have an M20 by 2.5, the 2.5 millimeter, that's the pitch. So what you need to do is fairly straightforward. You can either go 30 cosine, so there is that 0.866 number there, and you just times it by the 2.5 times 2.5. 2.16 is your thread height. So that means from the untruncated tip of the thread to the root of the thread, okay? So that your thread height would be 2.16 millimeters, and the rest of the digits just leave it on the calculator's display. That's thread height. That's not thread. That's not the clearance hole size yet, okay? So remember that 20 mils is also the nominal diameter. That's not the actual diameter of it. What I just measured here, that's the major diameter of a fastener. So a 20 millimeter bolt would be skinnier than this. Let me just draw another triangle here. There, and maybe tilt the camera a little bit. There. So on a thread, when it's done, the tip of the triangle is missing there, and the other tip of the triangle is missing there. So what that means is that let me see, that's still in picture. Okay, that's good, that's good. So this is my nominal diameter, in this case 20 millimeters with this M20, but my actual diameter, major diameter, the actual diameter of the thing is from the truncated tip of the triangle to the, on the opposite side of the fastener, the other truncated top of the thread triangle. Okay, it's going to be less than 20. It's going to be a little less than 20. Okay, so I just calculated that one thread height is 2.16. That's good. That's the 2.16 is the part that survives from here to here. Also on the other side, here to there. That's actually, sorry. That's not the part that survives. Sorry, that's the full height of the thread. My bad. That's the full from the top of the triangle to from the crest to the root. Okay. Now, like I said, 1/8 of this amount is missing from due to thread truncation here and thread truncation there. So 1/8, so 1/8 is missing on that side and 1/8 is missing on that side. So 1/8 plus 1/8 is 2/8, and 2/8 is the same as 1/4. Okay, so that means that 1/4 of my thread height, my actual thread height, is truncated away. Again, from the 1/4, 1/8 on one side and the other 1/8 on the other side. That's how this 1/4 came about. So what we need to do is that 20mm nominal diameter is being lessened by 1/4 of the thread height there. So the 2.16, that's why I left it on the display. If I divided this number by 8, I would just get one thread truncation that I have shown you on this phone there. I'm going to divide it by 4, equals a number 0.5. So the 0.5412 needs to be subtracted from the 20. And I'm just going to go 0.5412. So 20 minus 0.5412 equals 19.4588. 19.4588 millimeters. Alright, that's the clearance hole that the M20 by 2.5 thread needs. Just the bare minimum that any clearance hole would need to be drilled at, and that's the major diameter of the bolt. Like I said again, it's calculated, but it's more like an approximation because I didn't allow for a little extra the rounding part on top of the thread. So realistically it's more like 9.5, 9.6. Now that 1/10 of a millimeter is does matter, and you don't have a drill bit size 9.5 or 9.6 either, but anyhow, that's how the calculation is done. It's a pretty close approximation, just in case you don't have a clearance hole chart. Now next one is the tap size calculation. If you want to make a hole, so I'm just going to put this one aside. Tap size, I'm going to use this bolt here that I started with, this 7/16. So we're going to do one in Imperial. The tap hole size, okay, if you want to make a threaded connection and you have this bolt and want to thread it in there. Now normally you wouldn't do it with a motorcycle brake lever that you would be threading anything into it, but just work with the idea that you want to cut thread in there so that you can put this bolt into it. Okay, so that's what a tap hole size is. If the tap hole size is too big, the bolt is just gonna run through. That's a clearance hole. That's not good. Tap hole size has to be small enough for the full threads to be formed. The tap hole size need to run at the minor diameter of the bolt, which is best approximated or measured this way, but you can see right away that the jaws of the caliper here, where the bevel is on the caliper jaws, it doesn't quite, it's gappy, it doesn't quite fit inside the threads of this bolt, so I can't really measure the minor diameter of this one. But on a video I showed previously, I have arrows clearly indicating the minor diameter of the bolt. Anyhow, it's running from the root on one side to the root on the other side. And that's what the tap hole size should be. Now if you look at the size of this one, it says 7/16. 7/16, alright, but that's not the diameter. That's not the diameter of this one for the tap hole size. That's the outside diameter of it, the nominal diameter. You can see these two match. So 7/16 again would be this hole size, and not the hole size that goes to the root of these threads. Could be, okay, I can kinda show you something like that. My caliper is kinda just making it bigger. Yeah, okay, the distance between the caliper jaws now is just approximating there, just approximating the size of the hole that you need to drill for these threads to be cut into a hole so you can thread this one in. Okay, I hope that makes sense. Alright, let's do some math here real fast. Let's work with this. So 7/16 by, this is 7/16 by 14. That's the size of this thread on this bolt. Now that 14 is not pitch like we had on the metric. This is nominal diameter. That's a good start. But 7/16 is hard to work with. We need right away a decimal. So 7/16 is 0.4375. So the major diameter needs to be less, the nominal diameter 0.4375 of an inch. It needs to be lessened by a whole lot. I'll show you. I'm gonna draw this same triangle for the thread. It's on one side, and that's another equilateral triangle on the other side of the thread. And I'll show you. We need a hole that's about this big. That's gonna be the minor diameter on this thread, and I'll show you the detail for it. Let's go back to this picture. You can see that the bottom of the thread, this horizontal flat black line, solid black line, is part of this height. That's how it's laid out. So 1/8 of the height, of the full height, is missing due to the crest truncation there, and another quarter of this height is missing there at the bottom for root truncation, and so 5/8 of the height in the middle is left for thread depth that actually catches and grabs the mating threads together. Okay, now work with me on this one. Here's my little pointer here. 5/8 of the thread depth plus 1/8 of the thread depth. 5/8 plus 1/8 is 6/8. The equivalent fraction for 6/8 is, I'm just gonna write this one down. So we have 5/8 for thread depth plus 1/8 for crest truncation there. That's 6/8. That's the same as 3/4, 3/4. So 3/4 of the thread, the 3/4 of the thread here, thread's height, if I start grinding it from the untruncated height there, I grind it down to that point. 3/4 of the thread's height need to be ground down to arrive to that point that I need for the, for my minor diameter there. Alright, so, you know, if this was any simpler, there wouldn't be a trade shortage. So 3/4 of the thread's height, 3/4 height is missing there, and 3/4 of the height is missing there. 3/4 plus 3/4 of, okay, if you have 3/4 of a dollar in your left pocket and 3/4 of a dollar in the other pocket, together you have $1.50. That's 1.5 times the height of the thread. So you have to take the, I have lines everywhere. You have to take the nominal size 0.4375 inches, and this nominal thread diameter is being lessened by 3/4 there, 3/4 there, 1.5 times the thread's height. Okay, we don't have the thread's height, you need to calculate it. So that 14 isn't pitch, like last time we calculated it with pitch and everything. That's not pitch, that's TPI. So you're gonna have to calculate pitch first, and then you have to calculate height first. The height is calculated the same way, pitch times cosine 30, that's 0.866 amount that we used on the metric side. So pitch is calculated out of this very simply. You take 1 and you divide it by that 14, and you're gonna get pitch in inches. I'll show you that 14 means, if you look at it real close and you freeze the frame, I'm gonna set it to 1 inch, almost there, 1 inch, just lock it. There, over a distance of 1 inch, you have exactly 14 crests on this thread. And there you can see that the tip of the caliper is there on the first thread. Let me just put it on the first full thread. There. From there to there, I'm just rotating it a little bit so you don't have parallax, because it looks like I'm moving the caliper, but I'm not. I'm just rotating it. You can see 14 full threads on this one. Okay, so on 1 inch, in 1 inch you have 14 pitches. If you count the pitches, you're gonna have 14. So 1 divided by 14 is, I'm gonna write it above, 0.07. What's the rest of the numbers? 0.71428. Okay, let me just check it again. 1 divided by 14. Okay, 0.071428 inches. That's my pitch. I'm gonna leave it on the display. That pitch number needs to be multiplied by cosine 30. Instead of cosine 30, I'm just gonna go times 0.866, because that's the same number and close enough. Equals, I have another number, that's my height. This height needs to be times by 1.5 to get my full truncation. Okay, so I'm gonna go times 1.5. I have yet another number. That number is my total amount of truncation that's missing from there and from there. So now I'm down to this level and that level. So I need to subtract from 7/16 of an inch, which was that number, that one. I'm gonna write this one down. So as is, 0.4375 inches minus 0. That's where I started there. That's what I started writing there, but then a picture got in the way. 0.09278. That's enough digits. So 0.4375. 0.4375 minus 0.09278 equals that number, 0.34472 inches. So that's my minor diameter, that's my tap hole size. Okay, if you want to convert that number into 64th of an inch, because your drill bit sizes are in 64th, you just times it by 64 and you got 22/64. There's your drill bit size. Well, 22 over 64 is the same as 11/32, because those are equivalent fractions. So now you have it. That's your tap hole size for 7/16 drill bit. It's 11/32, and you can't measure it because the calipers don't get in there, the beveled portion. Okay, so you kind of have to either calculate it or look it up in a tap hole size chart, but if you don't have one, at least you have a fighting chance now. Okay, so that's the clearance hole and the tap hole size calculation. There, you have fun with it.